All right, everybody, welcome back again. I hope life is good with you and you're staying healthy and happy. I do miss seeing all of your smiling faces. And thank you for those of you who have been popping in during office hours. It's been great to see you and great to talk to you. I feel lately I'm spending a lot of time talking to myself, but then again, I am. So, pop in office hours and at least just say hello and let me know that you're doing okay. I hope everybody's doing okay. And if you're having any problems or issues, please don't hesitate to email me or talk to me, and I will do whatever I can to help you out. Today, we're going to be talking about fusion and fission. Fusion and fission are two types of decay. The first one we're talking about is fission. And they're not types of decay, they're types of nuclear reactions. So for that, I apologize. Again, I've been talking to myself for a very long time. Fission is what's happening in your nuclear power plants. Fission is what's happening in the atomic bomb. So nuclear power plants, atomic bomb. When you crack open that nucleus, you're releasing huge amount of energy. So this is like a decomposition reaction in chemical chemistry where we have one big atom and it's going to split apart into smaller atoms. Usually it's uranium-235, and we're going to bombard it with a neutron. That's how we get the split to happen. When uranium-235 is bombarded with a neutron, it forms krypton 92 and barium 141. But the cool thing about it is it's forming 3 new neutrons. Those 3 neutrons are then going to bombard 3 uranium atoms. Every time this nucleus splits, we're releasing a huge amount of nuclear energy. Now we have 9 neutrons. Those can bombard 9 uranium atoms. Then we would have 27 neutrons. And so we could bombard 27 uranium-235 atoms. Each time, exponentially, we're increasing the amount of energy that can be produced. And this is why the atomic bomb is so massive. And this is why we can produce a huge amount of energy in nuclear radiation and in nuclear energy from a nuclear power plant. But we're also creating a large amount of radioactive waste. In your nuclear power plants, to control the amount of neutrons, because it's those neutrons that are driving the reaction. We don't want the nuclear power plant to melt down or to blow up. A couple years ago, they had problems in Japan. Obviously, there was the big Chernobyl thing. And then 3 Mile Island didn't completely melt down, but they did release some nuclear energy into the air. So the control rods here, this is your reactor where the uranium-235 is. The control rods, which are made of graphite, are slid in and out to absorb some of those neutrons. And that way they control how much energy is being produced. All nuclear reactors are by an incredibly large body of water because they have to pump water through to cool the reactor. As this energy is going through, it's producing a huge amount of steam. The steam goes to turn the turbine. The turbine then creates nuclear power and electrical energy. So here's my electrical energy, which can then be used to light your house. Here is your house. Here's me, keeping a safe distance from your house, saying hello. It's been a long day. Miss you guys. All right. So it's producing electrical energy from a nuclear reaction. So the control rods are critical in keeping and slowing down the rate of that reaction. And the water cools it, but also then gets turned into steam. The steam turns the turbine then creates the electrical energy. So in a fission reaction, a big atom is being split and producing smaller atoms. So in fission reactions, you have a big atom being split and creating smaller atoms and then producing huge amounts of energy. Again, when we balance nuclear reactions, we balance mass and we balance charge. So top numbers have to equal, bottom numbers have to equal, and the arrow is your equal sign, just like it is in chemical chemistry. So here, if we were figuring out what goes there, we would need a number that plus 4 equals 238. So that's going to be 234. On the bottom, we need a number that plus 2 equals 92. So that's going to be 90. We look on the periodic table. Do not look at the top number. The masses can be different because each element has a specific number of isotopes. So we only look at the bottom number. That's going to tell us what element it is. So remember, identity of the element is determined by the number of protons. You change the number of protons and you change the element. So this is thorium. If we take a look at the bottom one, you need a number that plus 234 equals 234. So that's going to be 0. And a number that plus 91 equals 90. That's going to be -1. That's an electron. So we're balancing top numbers, we're balancing bottom numbers, we're balancing mass and charge. We don't look for the element by the mass because of isotopes. The masses can be different. We always look according to the number of protons. Fusion reactions are fusing together. So this would be like a synthesis reaction in chemical chemistry, where you've got an element plus an element, and now this is fusing together to make a bigger element. This is what happens on the sun. So on the sun, you have hydrogen with a mass of 2, and you have hydrogen with a mass of 3, okay? And it comes together to form helium with a mass of 4, and then huge amounts of energy. If you've never noticed it before, the sun produces huge amounts of energy. It's also producing massive amounts of helium. So I think if you were standing on the sun and couldn't get burned to death, your voice might sound a little squeaky, but I don't know that for sure. So in a fusion reaction, you're taking your two elements, you're adding them together, and you're forming a bigger element. This only occurs in incredibly high temperatures, like the sun. Unfortunately, we can't be on the sun, and we can harness the sun's energy through solar panels, but here on Earth. So scientists have been working for a very long time on something called cold fusion. They've made a lot of movies about it. I think there was a movie with Brad Pitt. I do remember Brad Pitt. We're talking a long, long time ago. I don't remember the name. I'll get back to you on that one. Anyway, cold fusion. So cold fusion, and scientists have been working on cold fusion for a very long time to get this type of reaction to happen, something at reasonable temperatures that we could use on Earth, because it's producing helium, which the world is running out of anyway. That's not radioactive. And so we're producing non-radioactive waste, and we have ample supplies of hydrogen. So it would stop the burning of fossil fuels. So maybe one day they will figure this out. Maybe one day I'll be let out of my house too. But for right now, social distancing. All right, let's practice some nuclear reactions and nuclear equations. Again, the arrow is my equal sign. I'm going to change colors here to something a little brighter. Let's go with the red. So, top numbers have to equal, bottom numbers have to equal. So I have a number plus 4 that has to equal 12 plus 1. So that top number, this is 13, This is 4. So this is 9. Top number over here is 9. On the bottom, I need a number plus 2 that equals 6 plus 0. So 6 on this side, this has got to be 4. I look on the periodic table, atomic number 4 is beryllium. For the next one, I've got a 1 plus something that has to equal 236. So that's going to be 235. That's a 235. Hold on, let me see if I can erase it and write this a little bit neater. All right, 235. On the bottom, you've got a 0 plus some number that has to equal 92. So that's got to be 92. And atomic number 92 is uranium. Again, not going by the top numbers because the top numbers are isotopes and those masses can change. You always determine your identity of your element by your bottom numbers. So I look on the periodic table, number 92 has a symbol of a U. That's uranium. Let's try the next one. So I've got over here a number plus 1 that equals 12 plus 4. That's 16, so this has to be 15. And on the bottom, I need a number plus 1 that equals 6 plus 2. That's 8, so this has to be 7. I look on the periodic table, number 7 is nitrogen, so I put a capital N. We're balancing according to mass and according to charge. Let's try the next one. So I need a number plus 1 that equals 3 plus 4. So 7, this has to be a 6. And then I need a number that plus 0 equals 1 plus 2. That's 3. This is lithium. Lithium is number 3 on the periodic table. So to figure out what the symbol is, you're always looking at the bottom number. The bottom number will tell you the identity of your element. Because remember, the identity of your element is determined by the number of protons. You change the number of protons, you change the element. Next one, we've got, what do we got? 7 plus 7 is equal to 4 plus question mark. 14, so this is 10. And on the bottom, 3 plus 3 equals 2 plus question mark, 6. So this is 4. Atomic number 4 is beryllium again. Last one. 3 plus 2 equals question mark plus 1. So that would be, I'm having a brain issue, that would be 4. That took a little too long. And 1 plus 1 equals question mark plus 0, so that would be 2, and that's helium. Okay, so that ends my little tutorial on how to figure out nuclear reactions. As always, office hours are on Bronco days, which is any day that I give you a chemistry assignment, from 9 to 10 a.m. and 1 to 2 p.m. Okay, come and see me if you're having questions. I'd be more than happy to see your smiling face. The Schoology code to get into the Zoom classroom? Nope. The Zoom code to get it is on Schoology, or it should be at the email that I emailed you this morning. Have a great day. Hope you're staying safe. Wash your hands. Miss you terribly. See you soon.